Welcome everyone, I'm Adam, and for this video, me and my groupmates Gabriel, Pavin, Ikshu and Toboka will be discussing the usage of differentiation and integration to solve real-world engineering problems. What is differentiation and integration? To simply put it, they are the fundamental concepts in calculus and helps us in understanding how functions change and accumulate over time. Now let us go into more detail about differentiation. Differentiation focuses on finding the rate of change of a function. It involves calculating derivatives to understand how a function's value changes concerning its input. For instance, with a function fx equals to 3x to the power of 2, differentiation finds its derivative f prime x equals to 6x, showing the rate at which this function changes.
Hello, I'm Gabriel. I will be discussing the integration part of this video. Integration involves finding the accumulation or total value under a curve. It helps calculate areas under curves and find total quantities. For example, integrating the equation fx equals to 6x with respect to x gives us the equation fx equals to 3x power 2 plus c, representing the accumulated value. These concepts are crucial in the fields like physics for motion analysis, economics for modeling, and engineering for solving complex problems.
Today we're going to learn how integrals or integration can be used in how we can find out the fluid pressure force on a dam. The formula we use here is this one given right here. So it is AB is basically the height or the depth you're trying to find your pressure at. So this is the P is your density of your water, G is your gravity, dy is the depth as a function of y, and wy is the width of y. How the force of the dam is being expressed as an integral. We have here a trapezoid dam. It has the upper width is 12, lower width is 16 meters, and the height is 9 meters. As you can see, there's water here, and that is a tree. So for the first step is to calculate the range of force. So we're going to be using the formula again from the top. This is our force, and 0 to 9 is our height, as you can tell from here, and 1000 is basically the density of water. This is your G, your gravitational potential. And we have our Y, and this is for our width. So for width, we don't know because it varies, right? As you can see, I've drawn out the dam again, and at this part, the width will be 1. If I go up here, about here, it's going to change again. We need to divide this trapezium into, let's say, a rectangle and 2 triangles. So now we can tell by doing some simple maths that since it's divided, we need to know the width of this triangle and this triangle, which will obviously be the same. So 16 minus 12 equal to 4, and then we have 2, so divide 2, 4 over 2. What we have to think is that our width here, it varies, right? So we need to resolve this issue by using the ratio method. So we're going to compare our total width of an area will be 12, that is the minimum from the top right here, plus whatever from here, because it varies. So let's use the ratio method to find, okay. So this will be, so we have the height, which is 9, right? The height of the big old triangle. And we have, this is 4 over 2. And we have, let's say the small one, the small height here is y. And this is width 1. We can't use w because we already used w. So this will be width 1. So ratio method will have 9 over 4 over 2 equal to y over width 1 is in terms of y. So width 1 will equal to 2y over 9. Now this is for, let's say this is only for one side, but this is an even trapezium. So there's 2 sides. So we use this and we plug it back here. So now we have 2 times 2y over 9. So our total width 12 plus 4y over 9. We have this equation right here. We can sub it into the formula we had earlier. You can start multiplying 1000 and 9.800. Put in the outside 0 to 9, and we shall have y multiplied by our equation from here. So 12 plus 4y over 9 y. So continuing with this, so we have our final answer as 5.8212 times 10 to the power of 6 newtons.
In this question, we will be finding the rate at which the power output is changing with respect to time. Therefore, we need to find dp over dt. We know that the flow rate is changing at a rate of 20 meter cube per second square, and that the height is changing at a rate of 3 meters per second. The power output is denoted as rho g q h, where rho and g has its respective values. To solve this question, we have to use the product rule, which is basically the sum of each function that is multiplied by the derivative of the other function. It is important to use this rule as it can be used to find the derivative or differentiation of a function given in the form of the product of two differentiable functions. Therefore, we get the expression of dp over dt as shown. We should then substitute the values provided by the question. Therefore, we then get dp over dt to be equivalent to 196,200 h plus 29,430 q. Here are the key takeaways, and this problem demonstrates how differentiation is able to determine changes in the rate of power output when variables such as the ones stated are changed, aiding in understanding system dynamics and optimizing performance.
To summarize, calculus is a tool used all over the engineering industry in civil, structural, mechanical, and aerospace engineering. It forms the basis of building, optimizing, and manipulating physical phenomena. Differentiation is important because it is used to find the rates of change of quantities, such as formulating equations of motion for mechanical systems. Meanwhile, integration is crucial in calculating the accumulated change computation and finding the areas and volumes of any shapes or buildings. This was evident in our example of the hydro dam.